Hello everyone, Victor is here, and in this video I want to talk about the E2 reactions, which is probably the best type of elimination reactions out there because it gives chemists a lot of control over the reaction outcomes. So the goal of the E2 reaction, like any other elimination reaction out there, is to rip something off our molecule and make a new pi bond. E2 is a bimolecular reaction, so similarly to the SN2 reaction, the rate of the reaction depends on both concentration of the substrate and the base. So we can have our substrate and we have our base. However, since an elimination reaction is not a substitution reaction, we are typically going to compare the E2 reactions to E1 reactions and not SN2 reactions. The big difference between E1 and E2 reactions is that E2 reactions have a concerted mechanism, so just like the SN2 reactions. So we're not really going to form any intermediates in this reaction whatsoever, and everything will happen in just one step. Thus, if I have some sort of generic molecule here, the way the reaction works is, first, the base comes along and finds the beta hydrogen that's on the adjacent atom to our leaving group. I mark my leaving group here as an X. Then, as my base is pulling off the proton, this will trigger a cascade of the electron density which will displace my leaving group from the molecule. Importantly, this all happens in one step, so as I've mentioned before, we are not going to form any intermediates here. And as a result, I'm going to see the formation of a new pi bond between the alpha and the beta atoms. So, for instance, let's look here at this reaction. Here I have the substrate, which is my bromocyclopentane, and my base, potassium tert-butoxide. And for the clarity's sake, I'm going to redraw my substrate in a full Lewis structure so we can see exactly what we are dealing with and where our atoms are. Here, the bromine in this molecule is the leaving group, so the carbon on which it is sitting is going to be our alpha carbon. Next, I need to find the protons on the beta carbons to see what sort of elimination products I can get in this reaction. And as in this molecule both of our beta positions are absolutely identical, I'm only going to focus on the one of them, as the other one will give me the exactly same product. Next, our base comes and performs the elimination reaction in one step. Notice that the potassium here is just a spectator ion. I'm not even going to show that in my reaction mechanism whatsoever because it's really not doing anything. And just like in the previous example where I used a generic molecule, here we too make a new pi bond between our alpha and beta atoms. Easy enough, right? So, are there any specifics that we need to be mindful about when dealing with E2 reactions? Well, yeah, of course there are. The first requirement is that E2 reactions require strong bases. Typical examples of those include various alkoxides like methoxide, ethoxide, tert-butoxide, etc. Our alkoxides will typically have some sort of alkali metal as a counter ion like sodium or potassium, and for our purposes the metal's nature is pretty much irrelevant, so they are interchangeable. Later on, once we start discussing more advanced concepts, the metals will be important, but for right now, they're just spectator ions. We're also going to see some amides like sodium amide, not so often, and LDA, which is going to be a more often guest in our reactions. Finally, we're also going to occasionally come across some exotic bases like DBN or DBU, which stands for diazobicyclononane or diazobicycloundecane correspondingly. Make sure you copy all of these bases down, as it's really important for you to know how our typical strong bases look like and be able to recognize them once you see them in a reaction. So here is another important thing about our bases. The size indeed matters. So we're going to split our bases into a small and a bulky category. And the reason for why it matters is that the bulky bases are extremely sensitive to the sterics around the leaving groups. Let me illustrate it with an example. Here I have the same substrate reacting with two different bases. And as we have the same substrate, we can potentially make two different alkene products in both cases, as we have two different beta hydrogens in our substrate, giving me the two of the following molecules as my products. The hydrogen A is sitting in the middle of the molecule, so it's pretty sterically hindered. So if I'm thinking about pulling off this guy over here, I have a lot going on around it. I have my group with the bromine, I have the rest of the ring, so it's kind of difficult to get to that place. This means that a bulky base, such as a third butoxide, will have a lot of troubles trying to reach to that position because, well, third butoxide is very bulky by itself. So instead, a bulky base will go after the less sterically hindered proton, such as proton B, which is sitting on the outskirts of the molecule. So if I'm trying to get to this guy over here, well, I barely have anything around it, so that makes it really easy to grab it. Thus, the more substituted double bond will be the major product if we use a smaller base, and the less substituted bond will be result if we are using the bulky base. You can also hear terms the Zaitsev product and the Hofmann product, which refer to two possibilities. The Zaitsev product is an alkene with the most substituted double bond, while the Hofmann product is an alkene with the least substituted double bond out of all possible alkenes that we can produce in a given reaction. In this case, we only have two possibilities, but theoretically speaking, we can have multiple possibilities. So the most substituted bond is going to be the Zaitsev, and the least out of all of them is going to be the Hofmann product. We can also explain this observation from the perspective of the reaction rates and energy diagrams. I know, everybody loves energy diagrams, but just bear with me. In the case of the bulky base, which is going to be my first case over here, where I have the energy diagram drawn for the bulky base. So in the case of this bulky base, the transition state for the reaction involving the proton A, and I'll remind you the proton A over here in the middle of the molecule, so that transition is very high in energy. And as that transition state is very high in energy, it means that going through that transition state will require a lot of energy. So the activation energy for that particular step is going to be relatively high, which means that in the case of the bulky base, the formation of the Zaitsev product, which is over here, is going to be extremely slow. Well, in the case of the smaller base, the transition state involving the hydrogen A or the proton A is significantly lower. So we're not going to have any problems going after the Zaitsev product here because it is more thermodynamically stable and the difference between the two transition states is negligible. Here is, however, another important requirement that we have for the E2 reactions, and that's the stereochemistry of the transition state. The requirement is that the proton that we are trying to pull off and the leaving group, our X, they must be antiperiplanar to each other. This requirement comes from the molecular orbital interactions in this reaction. In order to push our leaving group out of this molecule, we need to supply the electrons from the CH bond onto the CX sigma star antibonding orbital, and that's only possible if the CH bond is coplanar with the said sigma orbital. So if I have my electrons on the CH bond over here, it is coplanar with my sigma star orbital, so they have to overlap, they have to align with each other. This cascade of the electron density then results in the formation of the new pi bond. Thus, if I have the atoms that are not antiperiplanar to each other, if my leaving group and my proton are not antiperiplanar, you'll need to be able to rotate one of the carbons around to make them antiperiplanar. Otherwise, the elimination reaction is simply not going to be possible. Well, it is going to be impossible to have an E2 mechanism, that is, of course. We could possibly have the elimination occurring via E1 or E1CB mechanism, depending on the nature of our substrate. But the antiperiplanar orientation of the hydrogen and the leaving group for the E2 purposes is pretty strict requirement, so we cannot just skip or forget about that. So, for instance, let's look at this example over here. The substrate has a good leaving group in the form of the bromine atom. When it comes to the protons that are on the beta carbons, well, we only have one here, which kind of makes our life easier. And those two, the bromine atom and the hydrogen, actually are not antiperiplanar to each other. So let me illustrate that by drawing a Newman projection looking from the left. So let's imagine I'm standing in front of the molecule, and that's what I'm going to be seeing. The bromine atom and the hydrogen in this case, they are not antiperiplanar to each other, they're actually gauche to each other. which is a problem because we know that we need them to be anti for the reaction to occur. So what are we gonna do in this case? We'll rotate one of the atoms around. So let's rotate the front atom like this. Now, these guys are indeed anti-periplanar to each other, which means that the reaction is going to be possible. So here is the Newman projection for the product, and by comparing what we had before the reaction and how the process forces the atoms in the resulting product, we can see that we're going to end up with a very specific stereo configuration of the final product. And the important observation here is that the phenyl groups are going to end up cis to each other, while the other stereoisomer would be more stable because it will have the bulky groups further away from each other. It is not going to be formed, and the cis molecule will be only E2 product in this reaction. So if you don't have a hydrogen that is opposite or anti from your leaving group, make sure you do the Newman projection analysis. I can also guarantee that it is going to be on your next exam. This is such a classic aspect of the E2 reaction that every single instructor I've ever seen tests for it. This naturally also applies to cyclic substrates. So for instance, let's look at this example over here. By doing my preliminary analysis, we can see that we have the few protons in the beta position to our leaving group. Let's call them proton A, proton B, and proton C, so I color-coded them for the easier reference. As building a Newman projection for a cyclic compound is a little difficult, although quite doable, so you should probably challenge yourself to draw one. Well, anyways, so building a Newman projection for a cyclic compound is kind of difficult, so I'm going to make a chair conformation instead. In the left chair conformation, my bromine is anti to the HC in the methyl group. The methyl group is, of course, useless for us, but HC, the proton C, works for our purposes because we need a proton. In the right conformation, however, the only atoms that are anti to my bromine are the carbons of the ring itself, so no protons can be used from this conformation whatsoever. Notice, I don't care which conformation is more stable, I only care if I have an antiproton to my leaving group. The only time when I'll be considering the conformation stability is when I'll be discussing the reaction rates. Till then, the conformation stability is completely irrelevant to me. Like in this case, even though the right conformation is more stable, reaction is impossible from that conformation, so the fact that the conformation to the right is more stable is irrelevant for me. Thus, since we now know that only proton C is useful for us, we can proceed with the reaction, giving the final product looking like this. And like in the last example, this product is not going to be formed, even though it is more thermodynamically stable due to the more substituted double bond. And as you can see, the anti-requirement is a pretty big deal for E2 reactions, so always make sure you are checking for it before you propose your product, and don't just blindly go for the most stable product without doing the appropriate analysis, no matter how tempting it might be. Thank you guys for watching this tutorial till the end. I know it had a lot of new information. If you found it useful, give it a like, subscribe to my channel, and make sure to enable the notifications so you don't miss any of the future tutorials. Hope you are having an awesome day, and I'll see you in the next video.